Hello. Welcome to physics. Today we are discussed about the electrostatics. This is a third video lecture of electrostatics. Today we are discussed about the electric field and every concept about the electric field. And this is a most beautiful channel of the physics on YouTube. You are most welcome to here. Let us start one by one, step by step, each topic of the electric field. Right. Initially, we are discussed about the electric field due to uniformly charged rod. Electric field due to uniformly charged rod. Right. This is a uniformly charged rod and charge distributed as like this. Total distributed charge Q and total length of the rod L and lambda is a linear charge density. Find electric field at point A. This is a separation distance of small r. Find electric field at point A. Right. Solve this problem. This is a charge rod, uniformly charged rod, and from the x distance, dx thickness cut and amount of here dq. Calculate electric field at point A due to point charge dq. Electric field dE equal to k times dq divided by x square, because basic formula of the electric field E equal to k times q divided by distance square mean r square, right. And value of dq mean a small amount of charge dq equal to lambda times dx, and this value put here. Electric field dE equal to k times lambda dx divided by x square, and total value of electric field using integration function both side. Integration dE equal to integration k times lambda dx divided by x square, using limit from lower limit to upper limit. Lower limit is small r and upper limit r plus L, because L is a length of rod, mean lower limit is small r and upper limit r plus L, right. And E equal to k times lambda is a common factor outside, and integration x power minus 2 dx limit r to r plus L, using integration function and basic formula of the integrations as like x power n dx equal to x power n plus 1 divided by n plus 1, and using limit x1 to x2 mean upper limit and lower limit. In the situations, electric field A equal to k lambda x power minus 2 plus 1 divided by minus 2 plus 1 limit r to r plus L, right. And E equal to minus k lambda divided by 1 by x r to r plus L, and using limit E equal to k lambda 1 by r plus L minus 1 by r, right, negative sign, and E equal to k lambda, negative sign multiply inside bracket mean 1 by r minus 1 by r plus L, and r plus L, here r plus L minus r, right, and r plus minus cancel out to each other. E equal to k lambda L divided by r plus L, right, and q equal to lambda times L, and new value of electric field due to uniformly charged rod kq divided by r plus L. This is a formula of electric field as a given situation, as a given uniformly charged rod, right? Next problem. Electric field due to infinite charge rod. Due to infinite. Right. Suppose that this is a infinite charge rod uniformly as like this up to infinite and uniformly charge distributed as like this. From the Gaussian surface, Gaussian theorem, around the charge rod, consider virtual Gaussian surface cylindrical design, and if I want to calculate electric field at this region, this is a small r distance and the radius of the virtual Gaussian surface, cylindrical virtual Gaussian surface, and direction of electric field at this point along this directions dE, mean E, and a small amount of area vector dA along the same directions, and angle between both vectors theta equal to 0 degree because both are act along the same directions. From the Gauss theorem, right, electric flux phi E equal to integrations E dot dA cos theta, and here theta is equal to 0 degree and cos 0 equal to 1. Electric flux phi E equal to E and integration dA, right, and phi E equal to Q divided by epsilon naught, and Q divided by epsilon naught equal to E integration of dA, and integration of dA equal to A mean area of the cylindrical Gaussian surface mean 2 pi RH, and this value equal to H equal to L, and Q divided by epsilon naught equal to E times 2 pi RL, right. In the situations, value of electric field E equal to Q divided by 2 pi epsilon naught RL, right, and lambda equal to Q divided by L mean Q equal to lambda times L. This is a linear charge density, right, and using here then electric field E equal to lambda times L divided by 2 pi epsilon naught RL. L cancel out from numerator denominator, mean value of electric field E equal to lambda divided by 2 pi epsilon naught R. This is a formula of electric field due to infinite charge rod, right. Vector form of this formula, vector E equal to lambda divided by 2 pi epsilon naught R and R cap. R cap is a unit vectors, and vector E equal to lambda divided by 4 pi epsilon naught R and R cap, right. This is a formula of electric field due to infinite charge rod. And 1 PYQ problems of JEE Mains exam, right. Suppose that this is a uniformly charged infinite rod and charge distributed as like this, right. Lambda is a linear charge density coulomb per meter, right. and alpha particles move around the charge rod along the circular path as like this, alpha particles, right, with speed of v. Find the speed of alpha particle. Find speed of alpha particle as a given condition, right. Solve this problem very conceptually and very easy problems related to electric fields. When alpha particle move along the circular path, then centripetal force act, means centrifugal force Fc equal to mv square divided by r, and Coulomb force F mean electric force equal to electric field times charge, right, mean E times charge, and value of electric field E equal to lambda divided by 2 pi epsilon naught r, and put here lambda divided by 2 pi epsilon naught r times q. Q means charge of alpha particles and both force equal to each other. This is a centrifugal force and this is a electrical force, okay, right, mean mv square divided by r equal to lambda q divided by 2 pi epsilon naught r, and r cancel out to each other, and mv square equal to lambda q divided by 2 pi epsilon naught, v square equal to lambda q divided by 2 pi m epsilon naught, and v equal to square root of lambda q divided by 2 pi m epsilon naught. This is a speed of alpha particle when alpha particle move along the circular path around the uniformly infinite charge rod as a given problems. If we want to calculate frequency and time period of the alpha particles, frequency and time period of alpha particle, then using formula V equal to r omega, right, and V equal to 2 pi r divided by t, right, omega equal to 2 pi divided by t. Omega is a angular frequency, okay, of the alpha particles. This value put here mean 2 pi r divided by t equal to square root of lambda q divided by 2 pi m epsilon naught, and value of time period calculate from here, very conceptual. And for the next problem, electric field due to charge ring at axis of charge ring, electric field due to charge ring at axis of ring, right. This is a uniformly charged ring, right, and suppose that positively charged distributed, uniformly distributed, positively charged, uniformly distributed, and this is a center point and this is a axis point. Suppose that this is a distance x and calculate electric field at this point. Find electric field at point O. As given figure, right. Then in the situations, a small strip cut here for dq charge, and due to this small amount of charge, calculate electric field in this point, right? And direction of electric field just along this directions, because this is a positively charged, and value of electric field dE. Component of electric field with respect to angle, mean dE cos theta along the x directions, and dE sin theta along the vertical directions, and vertical component cancel out to each other, and net electric field along the horizontal directions. Suppose that this is a radius r, and this value is square root from the Pythagoras theorem, r square plus x square. Net electric field at the axis point of uniformly charged ring, right, along the x direction, integration of dE cos theta, right, and value of dE equal to k, a small amount of charge dq, divide by distance square, mean distance under root r square plus x square का whole squares, and a small amount of electric field due to a small element dq, mean k times dq divided by r square plus x square की power only 1, right, and this value put here. Value of cos theta from this right angle triangle, this is a angle theta, and here using the Pythagoras theorems, mean trigonometry functions, cos equal to base divided by hypotenuse, base mean x divided by hypotenuse, r square plus x square whole power 1 by 2, and both value put here in the integration formula here, mean electric field Ex equal to integrations of k times dq divided by r square plus x square की power 1 multiply value of cos theta, mean x divided by r square plus x square की power 1 by 2, and here is a same base and power add to each other. In the situations, electric field E equal to k and x divided by r square plus x square की power 3 by 2 multiply integration dq, and integration dq equal to q, mean electric field Ex equal to k qx divided by r square plus x square की power 3 by 2, right. This is a value of electric field at axis of the uniformly charged ring. For the center, mean x equal to 0, this is a uniformly charged ring, and this is a center point. For the center x equal to 0, charge distributed as like this, right. In the situations, value of electric field at a center point equal to 0, and for maximum value of electric field, x equal to plus minus r divided by root 2, and from the graph functions as like this. This is a x equal to plus r by root 2, and this is a x equal to minus r by root 2. Mean in this locations value of electric field becomes maximum, and at a center point value of electric field becomes equal to 0, right. And suppose that electric field at a center due to this diagram as like this, mean a small width cut in a uniformly charged ring. This is a width W, mean dx, right. In the situations, value of electric field only this segment, and this segment value of electric charge dq, and due to this segment only this segment, right, electric field along this directions E, and value of electric field due to this diagram at a center point mean E equal to k dq divided by radius, mean radius k squares, and dq equal to lambda times dx, and dx equal to width of the window, right. This is a window point, and here put dq equal to lambda times w, and electric field k lambda w divided by r square, and value of k mean 1 by 4 pi epsilon naught. Then new value of electric field lambda times w divided by 4 pi epsilon naught r square. This is a value of electric field due to uniformly charged ring at a center point as a given situation, as a given diagram, as like this, right. And let us discussion start for the next problem, electric field due to uniformly charged spherical cell and also sheet, right, mean electric field due to uniformly charged sheet using Gaussian theorem, and as like this, suppose that this is uniformly charged spherical uniformly charged sheet, rectangular or can be square design as like this, right, and charge distributed uniformly as like this, and electric field in this point, and similar both side, left and right side. In this region, electric field and area vector along the same directions, vector E and area vector, this is a first point and this is a second point, and area vector along the same directions along the electric field, and similar here vector E and area vector of the small part of the charged spherical sheet, charge rectangular sheet, not spherical, right. From the Gaussian theorem, Gauss theorem, electric flux passing from the charge sheet, electric flux phi E equal to total value of electric flux from left side and from the right side. First E dot dA cos 0 plus second integrations E dot dA cos 0, right, because angle here theta equal to 0 degree and theta equal to 0 degree for the both side, and electric flux phi E equal to E integration of dA first plus E integration of dA second, and value of integration of dA equal to first integration of dA second equal to A, right, and electric flux phi E equal to EA plus EA mean 2 EA. This is a value of electric flux, and phi E equal to Q divided by epsilon naught mean Q divided by epsilon naught equal to 2 EA. E equal to Q divided by 2A epsilon naught, and sigma equal to surface charge density Q divided by A surface charge density, and E equal to sigma divided by 2 epsilon naught. This is a value of electric field due to charge sheet, infinite uniformly charged sheet. Some numerical problem related to this. Example, suppose that this is a charge rod and this is a second charge rod uniformly. Here negative charge distributed, surface charge density plus sigma, and here minus sigma, right. Find electric field at point A, at point B, and at point C. Electric field at point A, B, and C. In these situations, initially we are solve the value of electric field at point A. For point A, the direction of electric field due to this plate E1 and due to this E2, and direction of here at point A due to positive charge along this directions mean E1, and due to negative charge plate along this directions, and E1 and E2 act just opposite direction E1 and E2. E1 act along this directions and E2 act along this directions, and net value of the electric field, net value of electric field EA equal to E1 minus E2, and magnitude of the electric field E1 equal to sigma divided by 2 epsilon naught, and E2 equal to sigma divided by 2 epsilon naught, and total value here mean net value of the electric field at point A as a given diagram means sigma divided by 2 epsilon naught minus sigma divided by 2 epsilon naught, and total value of electric field at point A becomes equal to 0. And similar for point B. For B point, direction of electric field due to positive along this directions mean E1, and due to negative along this directions, right, and both electric field act along the same directions mean EB equal to E1 plus E2, right, and sigma divided by 2 epsilon naught plus sigma divided by 2 epsilon naught, here sigma divided by epsilon naught. This is a net value of electric field between both plates as a given situation. And finally at point C, EC equal to, for the C point, direction of electric field E1 along this direction because this is electric field due to positive plate, and direction of E2 along this directions. Both are opposite directions mean E1 minus E2. In the situations, value of electric field sigma divided by 2 epsilon naught minus sigma divided by 2 epsilon naught and becomes equal to 0. Mean outside of the both plates electric field must be equal to 0, but inside of the electric field sigma divided by epsilon naught. This is a best example of the capacitor, mean both plate of the capacitor electric field sigma divided by epsilon naught, right. And for the next problem, electric field due to spherical cell, right. Electric field spherical cell conducting spherical cell. In this situation, charge distributed only surface area as like this, and initially we are calculate electric field outside of the charge surface. This is a radius and this is a small r, and want to calculate electric field in this regions, right, in this point. Right, in this point. Then value of electric field at this point in first when small r is greater than as compared to capital R, from the Gaussian theorem, right, electric flux phi E equal to integration of E dot dA cos theta, and theta equal to 0 degree, mean q divided by epsilon naught E outside and integration of dA, right, and integration of dA equal to virtual Gaussian surface for the small r radius, mean 4 pi r square, and q divided by epsilon naught equal to E out and 4 pi r square. Value of E out q divided by 4 pi epsilon naught r square. This is a value of electric field outside from the charge surface. And vector form of the electric field, vector E out equal to q divided by 4 pi epsilon naught r square r cap. And second point, electric field at charge surface, right, and for the charge surface small r equal to capital R, electric field at a surface equal to q divided by 4 pi epsilon naught r square and r cap, right. This is a formula of electric field at a charge surface. And inside electric field, inside of the surface, mean small r less than as compared to capital R. In the situations, inside no any electric field, because total charge distributed on the surface area of the conducting spherical object, and inside no any electric field, q inside equal to 0, right, and no any electric field. In the situations, graph of the electric field, this is a center point and a small r equal to 0, and from center to surface, mean inside region electric field equal to 0 and charge inside equal to 0, and this is a surface point, and graph as like this: inversely square proportionals E out inversely square proportional to R square. This is a graph relations of the electric field due to charge spherical conducting object, right? Suppose that electric field due to insulating charge spherical object, right? Then in this situation, say the charge distributed in a whole volume as like this, and this is a radius capital R. Initially we calculate electric field outside in this region, and total charge and surface volume charge density rho equal to charge divided by volume. Volume mean 4 by 3 pi r cube, right? Initially we calculate electric field outside, of the charge surface, right? Mean E outside, where small r is greater than as compared to capital R from the Gauss theorem. Right, from the Gauss theorem, electric flux mean Q divided by epsilon naught equal to integration of E dA cos 0, because positively charged and direction of electric field area vector both are act along the same directions. Q divided by epsilon naught equal to E out and integration of dA. Integration of dA equal to 4 pi r square, and the value of E out equal to Q divided by 4 pi epsilon naught r square. This is a value of electric field outside, and at surface small r equal to capital R, surface equal to Q divided by 4 pi epsilon naught r square. This is a value of electric field at a charged surface, second point. And third point, electric field inside, of charge spherical object, mean charge surface, right? This is a uniformly charged sphere, insulating sphere, and total charge Q distributed uniformly. And suppose that calculate electric field in this point, and a small r region spherical object, and in this region value of electric charge Q dash for the constant volume charge density, mean charge divided by volume, mean 4 by 3 pi r cube equal to Q dash divided by 4 by 3 pi r cube, right? And Q dash here mean small r cube divided by capital R cube multiply q, and using the Gauss theorem, from the Gauss theorem, mean q dash divided by epsilon naught equal to integration of E dot dA cos 0, and value of electric field inside equal to q dash divided by 4 pi epsilon naught r square, and value of q dash put here, then value of electric field inside region mean 1 by 4 pi epsilon naught r square, and q dash r cube divided by capital R cube multiply q, and here cancel out because r square here and r cube mean q times r divided by 4 pi epsilon naught r cube, and for the center point, right, small r equal to 0 and E center equal to 0, mean electric field inside directly proportional to r as like this from this formula, right, and for the graph relations, here electric field E and here distance r. Electric field from center to surface directly proportional. This is a center point, and electric field inside directly proportional to r, and this is a surface point. Here small r equal to capital R, and graph as like this, E out inversely square proportional to distance, right. And for the next problem, electric field due to non-uniform insulating spherical object. This is a non-uniform insulating spherical object, charge distributed as like this, right, and for the non-uniform, rho equal to mean rho r equal to rho naught r power n. Calculate electric field in this point, inside mean at point A. Find electric field at point A, right. In the situations, the small amount of charge in this region, mean dq equal to rho r mean volume charge density multiply volume, right, volume only in this region, right, and dq equal to rho r equal to rho naught r power n, and volume 4 pi r square dr, because this is a radius and dr is a thickness of a small spherical object as like the layer of onion, right, and electric field, now electric field inside region E equal to, right, integration of k times dq divided by r square, and value of dq put here, electric field E integrations K and value of dq rho naught r power n plus 2, because here n power and here 2 power, and 4 pi, right, dr. This is a value of electric field, and divide by r square, right, E equal to k rho naught 4 pi and r power n plus 2 divided by r square dr, using limit from 0 to capital R, right, and value of electric field equal to 4 pi, arrangement of this formula, rho naught times k, and here r power integration r power n dr, limit 0 to r, E equal to 4 pi rho naught times k and r power n plus 1 divided by n plus 1, using limit 0 to capital R, and here E equal to 4 pi rho naught k divided by n plus 1 and r power n plus 1. This is a formula of electric field due to non-uniform, right, non-uniform spherical insulating object, right. In this situations, this is a electric field at a surface point, at a surface point. This is a surface point, right.